In the second pseudo experiment, I will show you the structure of water around different solutes. For water, I will use the SPCE model. It's a classical model, probably one of the simplest ones, but still good enough. It's an acronym for simple point charge and extended, like sort of second generation of this model. And for solutes, I will use the Lennard-Jones potentials plus charge. For fullerene, the charm 21 force field. All simulations will use the Rayleigh or leapfrog integrator. The time step is 2 femtoseconds. For water, we need to keep the bond length and angles fixed. It's a rigid model, so shake is used. The cutoff will be smoothed, which is a bit compromised, but it's faster. And the Berenson thermostat and barostat will be used. To run these simulations, there are several steps needed. First, a configuration will be prepared by random shooting of both water molecules and the solute. Then some time is needed for equilibration. This equilibration has several parts. In the first part, the times constant of the thermostat is very short and no barostat is turned on. Then the barostat is turned on and we need to simulate for some other time to equilibrate. And then to run the productive run. Then I will show you the radial distribution functions and the running coordination numbers, and we can also observe the structure graphically. Let's choose the lithium cation, the first system to simulate in water, and now the script prepared lithium in a box of 200 water molecules at constant volume. It's seen that it's not fully equilibrated, but we will continue by an NPT simulation that is at constant pressure. It'll be a bit more, a bit slower, but not so much. Okay, so it doesn't look so bad. I would say it's almost equilibrated, good enough for us. So let's go for the productive run. Now an NPT simulation is running with one lithium cation in water, and here we have the results. First, I will show you the trajectory. Actually, not too much is seen here. So let's show the convergence profile. Well, they look pretty well. So the radial distribution functions. And we can see here a very high first peak. It corresponds to the radial distribution function lithium-oxygen. It's not surprising because lithium is positively charged and is small, so it's attracted to the negative oxygen. And also we can see here that the minimum is very deep. Essentially it's almost zero. It means that these water molecules around lithium are not exchanged so often. They are kept very firmly near lithium. Okay, so let's go back here. It may be interesting to watch the hydrogen lithium radial distribution function. It's farther away. That's because, of course, the water molecules around lithium are oriented by oxygen towards this lithium cation, but there are two hydrogens attached there, and these are visible here, a bit farther from lithium. The minimum is quite low, but not so low as with oxygen lithium. Okay, so let's have a look at the running coordination numbers. We can see here a very flat inflection point for lithium oxygen. It means that there are 4 oxygens around lithium. 4 water molecules in a solvation shell of this model of lithium. But in this case it's quite realistic. Lithium is very small, so only 4 water molecules can be arranged around one lithium cation. Not surprisingly, if we take lithium hydrogen here, we'll get about a double, but it's a bit more. It means that we have some other hydrogens from other water molecules than from the first solvation shell that are pretty close to this lithium. It may happen if you imagine that such a solvation shell around lithium has a special shape, and there are still some space around for another hydrogen to fly around, but not more than one. Okay, this was lithium, but let's have a look at the solvation shell. I will choose here certain distance around the lithium ion. It will be 5 angstrom around, but I will show also the hydrogen bonds. And to show the hydrogen bonds, we need the good distance how to define the hydrogen bond. It will be defined by the hydrogen-oxygen bond, not within one water molecule, but between 2 different water molecules. That is the minimum at the radial distribution function hydrogen-oxygen, and this minimum is about 2.4 angstrom. So here you can see lithium, green are hydrogen bonds, and you can see that really there are 4 oxygens, 1, 2, 3, 4, arranged approximately tetrahedrally around one lithium. I can change here the shell which is shown. So here we can see only those 4 water molecules, and also they move in time. So this is the trajectory, not the first one. So I can go perhaps by 1. Sometimes they are farther, so we can see another water molecule. I can show less of them. So the system is alive. There is movement, sometimes even exchange between these water molecules, but not so often. And I can increase this shell, so now we can see a lot of water molecules around, and the system of hydrogen bonds around such a small positively charged solute as the lithium atom. So let's try this again with something else. Let's try chlorine. It's negatively charged. So again, we go through the same steps. So equilibrating at constant pressure. Already quite well equilibrated. And so we will not repeat equilibration and the simulation. Okay, looks slow, but actually it's much faster than it was 10 years ago. Now you can see the trajectory. Chlorine is larger, is depicted larger, and it means that the Lennard-Jones sigma is larger. This is the convergence profile, so it isn't so bad, and the radial distribution functions. Again, we can see here 2 functions with large peaks. It is chlorine hydrogen, and now it's at a quite short distance, and it's quite high. Of course, chlorine is negatively charged, so that the water molecules around chlorine are oriented by this hydrogen towards chlorine. But the chlorine atom is larger than oxygen atom, so that here we have hydrogen-oxygen radial distribution function, and this peak is closer. The distance of this hydrogen bond is shorter than the typical distance hydrogen chlorine. Here we can see, I forgotten this to mention in the last simulation, the minimum on the hydrogen-oxygen distribution function is at about 2.4. So it was the limit by which we defined the hydrogen bond between hydrogen and oxygen of water molecule. We can see here the pink or purple curve. It corresponds to the chlorine-oxygen distribution function, and you can see that it's farther from oxygen. Now, of course, oxygens are negatively charged. The chlorine anion is also negatively charged, so that they repel each other. And we can also see here that these minima on the distribution functions are quite low. It means that we will get quite reasonable cumulative distribution function, or the coordination number. So let's have a look at the coordination numbers. Again, we have here chlorine hydrogen, and the typical coordination number here is about 7. That is, we have on average 7 hydrogens around chlorine, 7 water hydrogens. And how many do we get for chlorine oxygen? It's again about 7, this pink curve. It means that we have on average 7 water molecules around chlorine. Of course, this means on average. It may be 6, it may be 8. It depends on a random factor they exchange, and we saw on the graph of the radial distribution function that the minima aren't so deep as for lithium and oxygen, so that the exchange is much faster now. Also, this means that we have here chlorine and hydrogen. We have also second hydrogens about the same water molecule, but it is farther away, so it doesn't come into this plateau, into this inflection point. And why it is seen? Because this coordination number of oxygens around chlorine is about the same as of hydrogens about chlorine, and it means that the second hydrogens of water molecules are somewhere farther away. They are not counted twice here. So the typical configurations likely here are that we do not have 2 hydrogens of a water molecule, of the same water molecule, attracted to the same chlorine. But let's have a look at the solvation shell. Whether it's true what I have said. So I now depict only the closest water molecules, and we can see that really we have 2, 3, 4, 5, 6 water molecules around, and that's the 7th one. So let's change the configuration, and it looks approximately the same. The last configuration has again 7 of them. Of course, it may change to 6 now. I can increase the number of them. Oh well, so there are 6 just at the point of exchange of a water molecule. We can show more hydrogen bonds around such a cage, and this cage is organized in such a way that both hydrogens are attracted to chlorine and the rest engages in hydrogen bonds. There may be exceptions. Sometimes we can see here, I cannot find it anymore, that we had one water molecule that was approximately attracted by both hydrogens, but it's rare. Which one? Yeah, well, no, I cannot find it right now. Never mind. So let's finish with chlorine, and let's use, let us say, argon. It's small, but it's not charged. So once again, the same procedure, NPT simulation to equilibrate. Well, should be equilibrated more, perhaps, so let's try once more. But probably the difference will not be okay. So the simulation, argon in water, and to show how it looks like, argon is again green. The convergence profiles look well. The radial distribution function, and what we can see here, we have quite a wide peak of argon and oxygen, and also quite a wide peak of argon and hydrogen, so that neither oxygen neither hydrogen is attracted to the argon atom. Okay, so the cumulative distribution functions don't show any strict structure or any pronounced structure. Actually, both of them, it's green and pink, grow smoothly, and we do not have any inflection point because we didn't see any minimum or any pronounced minimum of the radial distribution function. So actually we cannot determine the number of neighbors. They are organized very smoothly around such an argon atom. We can depict the solvation shell again. Again, I will decrease the number, and what we can see here, different water molecules are at different distances. We cannot fix the distance of showing water molecules about the argon atom so that we could determine a clear shell. So this is how it looks like during the simulation. We have water molecules, perhaps I will decrease this. We have water molecules that are oriented in parallel to this bit, oriented with hydrogen towards, and so on. Mostly will be plus minus tangential around this argon because they will be engaged in hydrogen bonds with other water molecules. And that's all for this simulation. Thank you for your attention.